This video presents the work Auto-Encoding Bayesian Inverse Games, a framework for tractable Bayesian inference of unknown parameters in non-cooperative games. When multiple agents interact in a common environment, each agent's actions impact others' future decisions. In many settings, agents must account for this coupling when competing to achieve their individual objectives. Imagine a robot interacting with a human driver at an intersection, where they both wish to reach their own goal while remaining safe. Dynamic non-cooperative game theory naturally frames multi-agent decision-making as coupled optimization problems. In this framework, agents optimize their individual objectives while considering each other's future decisions and respecting constraints. However, complete game models are often not available in real-world scenarios. For example, at the intersection, the robot may not know the human's goal. In this work, we solve the inverse game problem in a Bayesian framework to infer the posterior distribution over unknown game parameters from observed behavior. The inferred posterior can be used to inform downstream tasks, such as forecasting human trajectory distributions or uncertainty-aware game-theoretic planning. In theory, one can compute the posterior over game parameters via the Bayes rule. However, several challenges exist. First, the prior distribution of the unknown game parameters is usually unavailable. Second, the observation model is complex in this case since it involves the solution of a dynamic game. Distributions thereafter typically are not available in closed form. Finally, for continuous distributions, the marginalization involves an intractable integral over the game parameter space. To enable tractable solutions of Bayesian inverse games, we present a framework that embeds a differentiable game solver into a variational autoencoder to approximate exact Bayesian inference. The approach learns the posterior computation from unlabeled interaction data. At training time, for each observation, an encoder model predicts a latent Gaussian posterior approximation. Latent samples Z drawn from this distribution are then mapped through a decoder model to the game parameter space. Since the decoder model is a flexibly parameterized nonlinear function, our approach can capture non-Gaussian and even multi-modal posterior distributions over the game parameter space. In a final decoding step, a differentiable game solver computes Nash equilibrium trajectories based on the predicted parameters to recover the observations. The entire pipeline is end-to-end differentiable for unsupervised gradient-based training. Note that, in order to take samples from the inferred posterior, no additional game solves are required at runtime. For example, in the intersection problem shown on the left, the generation of 1,000 samples takes about 7 milliseconds. We compare our framework with existing non-Bayesian inverse game solutions. In contrast to our approach, the baseline greedily maximizes the observation likelihood, which ignores the underlying prior distribution. Furthermore, instead of posterior distributions, the baseline only gives point estimates without information about uncertainty or multimodality. We show a comparison of the two inference approaches in combination with existing game-theoretic planning methods in the intersection driving scenario. First, we show the ground truth behavior generated by assuming a known human goal. Our approach recovers multimodal posterior distributions that accurately capture the uncertain human goal and enable safe and efficient downstream motion plans. By contrast, the baseline often predicts inaccurate goal estimates since it ignores the underlying prior distribution. Furthermore, the point estimates can cause overconfidence in downstream motion plans and therefore increase the risk of collisions. In our paper, we perform extensive quantitative evaluations of our approach, demonstrating its ability to capture multimodal prior and posterior distributions. This capability further enables safer motion plans compared to non-Bayesian inverse game baselines.